Okay, I'm going to start now. So, one important part of computational combinatorics is a few identities, which relate to the choose function. One second. Okay, they relate to the choose function, where n choose k is the number of ways to pick k items out of n. And one of the identities is that n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. Another is that the sum of n choose 0 plus n choose 1 until n choose n is 2 to the n. Then there is the hockey stick identity, which states that n plus 1 choose k plus 1 is n choose k plus n minus 1 choose k, etc. until k choose k. And the last one is van der Waals identity, which states that the summation of I'm actually going to write it like um, m plus n choose k is equal to m choose k n choose 0 plus m choose k minus 1 n choose 1 until m choose 0 and choose k. And these are important identities to know, but it's also as important to understand why these are true, because sometimes the intuition from this will help you solve even different problems. So for the first one, you can think about how to choose k plus 1 elements out of n plus 1. And we can think about if we include n plus 1. If we don't, then out of the first n elements, we will be picking all k plus 1 of them. If we do include n plus 1, then we will only be picking k out of the first n. So we have two cases which contribute these two terms. And this is the type of thinking that will be used for all of these identities. You think about what one of the sides represents, and you see how that splits into the other side. And for the second one, we can think about how many ways can we pick any subset of the n elements. So this is equal to 2 to the n because for each element, we either include it or don't include it, and that contributes two possibilities. But also, we have at most n elements that are being picked, and if we pick k elements, the number of ways to do this is n choose k. So we can think about picking subsets, and we can think about what are the sizes of the subsets. For the hockey stick identity, it's more similar to the first one, where we think again about picking k plus 1 elements out of the first and out of any n plus 1. And the argument is very similar as before, but instead now we consider the last elements that we pick. If the last element that we pick is n plus 1, then as before, we will be picking k out of the first n. But if we don't pick n plus 1 and we do pick n, we now are choosing k out of the first n minus 1, etc. And if the last element is m, there are in general m minus 1 choose k ways, because everything after m is not included, but out of the first m-1 elements, we have to pick k of them. And for the Vandermon's identity, this one is where I think knowing where this comes from is the most important, because sometimes the exact same idea shows up as a problem. You can think about if you have red items and n blue items. And how many red items do we pick? However many we pick, we are picking k minus that many of the blue items. So let's say we pick I red items, then we are picking k minus I blue items. And there are choose I ways to do the first, and choose k minus I ways to do the second, which is how we recover the summation. And here we can see an exact example of Vandermon's identity appearing. It's even formulated in the same way with two different categories of things being chosen. But here we have a restriction. So what the problem is saying is we have 11 men and 12 women. We pick some number, let's say k of the men, and then we pick k plus 1 of the women. And we only have the restriction that k is between 0 and 11, which is implied anyway. So this is all we need to worry about. And we want to find the number of ways we can do this. So by definition, this is 11 choose 0 times 12 choose 1 plus 11 choose 1 times 12 choose 2 until 11 choose 11 times 12 choose 12. And this sort of looks like Vandermon's identity, but it's also different because here these two add to the same number, but here their difference is the constants property. So to deal with this, we can recall that n choose k is equal to n choose n minus k. And this is because if we are picking k elements that are going to be included, that's the same as picking n minus k elements that are going to be excluded. So we can, instead of thinking how many women we pick, we can think about how many we don't pick. Then we have 11 choose 0 times 12 choose 11 plus 11 choose 1 times 12 choose 10 until 11 choose 11 times 12 choose 0. And by Vandermon's, this is 11 plus 12 choose 11, which is 23 choose 11. And in the problem, they ask you to find the sum of the prime numbers that divide this, which is just by writing out the formula as 23 factorial over 11 factorial times 12 factorial. But this is tedious and not really combinatorial, so I'll leave it out. So that is the fundamentals of combinatorial identities. Another very important topic to computational combinatorics is what's is called linearity expectation, but does not always need to deal with expected values. So this is a concept that I think is best explained through examples. And one of the most standard examples for this is if you have 100 students sitting in a circle. For simplicity's sake, I'm only going to draw 4. And let's say this is A, B, C, D. A picks randomly between B and D with 1/2 chance for each and throws a snowball at one of them. B picks randomly between A and C and throws a snowball at them. Then C does the same and D does the same. And we want to think about how many students are completely untouched. In this scenario, the answer is 1, which is D. And we want to think about on average what this is. And this is a problem that's very hard to tackle because there's too many variables in where each student throws a snowball. So instead, we can think about this for one specific student. So they have two neighbors and they are not hit with probability 1/4 because they're only not hit if each of their two neighbors picks the other person to throw a snowball at. And the fundamental idea of linearity of expectation is that to recover the answer for all 100 students, you can just take 1/4 and multiply it by 100. And the reason this is true is because although it although one student getting not hit can influence another student getting not hit, since you're taking the average, you can separate the possibilities in terms of each student and add them up in that way. And another standard example of this deals with permutations again. So I don't think I've used the term permutation yet. What it means is that you reorder the n numbers in some way, and then let's say we have 1, 2, 3, 4, and we randomly reorder them. One way we can do this is 4, 2, 1, 3, and this is a possible permutation. There are n factorial permutations because that's the number of ways we can order these numbers. And we want to think about the number of fixed points, which is when a number appears in the same place, both in 1, 2, 3, 4, and in this permutation. Here, the only example of this is 2, which appears in the second place both times. And again, we can think about this through linearity of expectation. Each number is fixed with probability 1/n because it can go to any of the n spaces with uniform probability and only one of them is correct. So the total number is n times 1/n equals 1. And this is a very surprising result that is extremely hard to derive without using this kind of reasoning. But by considering it by linearity of expectation, we can drastically simplify the problem. And this problem actually is fun to think about in a more general case. So here, an example problem is if you instead consider the average number of cycles, which is when you have something like, uh, let's consider this example. 4 is in the first spot. Now we look at 1, which is in the third spot. And 3 is in the fourth spot. And 4 is already seen. So we say that 4, 1, 3 is a cycle of length 3. And you want to find the average number of cycles of a certain length when you take a permutation. The idea is pretty much the same. It does have a few more details, but it's a fun exercise to think about. And another application of this linearity of expectation idea showed up on the 2022 AIME at number 12. Here we are considering over all sets, all pairs of sets, the size of their union. But we also have this restriction that the two sets have the same size. And we have a size of a union, which is quite annoying because we don't know anything about what that union is going to look like. So instead of using the size of the union, we think about when is each element in the union. We can think specifically about one. It doesn't really matter too much which one we choose. So there are n minus one other elements. And one is in the union of these two subsets, only if it's in both of them. And other than that, the two subsets have some amount of these n minus one other elements. They also have to have the same size as specified in the problem. So we want to find the number of A, B that are subsets of 1, 2 until n minus 1 of the same size. And this is how we reduce a very ugly condition about the size of a union to a much more nice one about subsets of a certain size. It's still quite complicated to finish from here, but it actually is helped a lot by the Vandermonde intuition from before. So we have subsets of some size k. And then there are n minus 1 choose k ways to pick A, and then n minus 1 choose k ways to pick B. But actually, since this isn't in the Vandermonde form, but it's very close to it, as before, we instead consider the complement of B, which means everything that isn't in B. Um, then that would be n minus 1 choose k times n minus 1 choose n minus k minus 1, which you can compute using Vandermonde. And sometimes I don't really like to keep writing out the product of these numbers. So I just think about this directly in our original question. Here, A is a subset of 1 to n minus 1, and B is a subset of 1 to n minus 1 as well. And their total size is n minus 1. So if we think about this through Vandermonde's, we will get that the answer is 2n minus 2 choose n minus 1. And then we still have to multiply this by n because we are considering this for one specific element, but we care about the entire size. Now that we have an explicit formula for the answer, again, we have to plug it in for 2022 and 2021, which can be a bit annoying, but this is feasible. And it's not very combinatorial, so I'll leave it out. Okay. Another important concept for computational combinatorics are specific sequences. So one such sequence is the Fibonacci sequence. The idea is you have this recursive formula, Fn plus 2 equals Fn plus 1 plus Fn. And you have a starting condition, and it's actually, I don't know if it's usually described as this or as this, but I prefer using the former, so that's what I'll go with for now. And the first few terms can be computed using the formula. They look like this. And the Fibonacci sequence shows up in many places. You can also compute a closed form formula of it by trying to express it as A r1 to the n plus b r2 to the n, where r1 and r2 are roots of x squared equals x plus 1. This is not necessary for the talk and also a bit complicated, but if you're interested about this, I believe it is called characteristic polynomial, and the resulting closed form is called Binet's formula. Also, if you're interested in linear algebra, you might recognize this term from matrices. In fact, this is because if you try to think about this relation as a matrix, the characteristic polynomial will be the same as the characteristic polynomial of that matrix. But again, that isn't very relevant to the talk. It's just in case you're interested in this. And I think the main thing to be able to do for the computational combinatorics problems is recognize this relation and sometimes be able to recognize a few of these numbers. And I'll get to why in a bit. A similar sequence is the Lucas sequence, where it has the same relation. And the starting conditions, I don't remember which indices they were. I think it was L0 equals 2 and L1 equals 1. And I actually don't understand too well why this shows up in some places, but it does appear sometimes. And again, I think the most important thing to know is a few of these starting values. But I think the most interesting sequence to know for computational combinatorics is the Catalan numbers. There are a few ways you can think about these. So one way is if we have a grid of n points. So this is n, this is n. Actually here n equals 3 because this would be 0, this is 1, this is 2, and this is 3. And we can think about the number of paths from 0, 0 to 3, 3 that never go above, and this is strictly above, so it can be on the diagonal, but they never go strictly above the diagonal. And to think about this, it's important to recall that without the restriction, the answer would be 2n choose n. And this is because we have to move to the right n times, and we have to move up n times. And it's just the number of ways to order these, which is 2n choose n. And the way to think about how many of these there are is actually very neat. So you can consider a path that goes above the diagonal at some point. Let's say it goes up here. We have some path for the rest of the time that goes up from 0, 1 to n. Now flip every up move and right move. So what that means is that if you have a sequence where, let's say you go up, let's say you go right, right, up, right, up, you instead go up, up, right, up, right. And since the original path did plus n minus 1, this will do plus n minus 1 n, and we will reach n minus 1 n plus 1. And it takes some effort, but it's not too hard to show that paths from 0, 0 to n minus 1 n plus 1 are in unique correspondence with the bad paths from 0, 0 to n. And from there, the number of good paths would be 2n choose n, which is the number of total paths from 0, 0 to n, minus 2n choose n minus 1, which is the number of paths from 0, 0 to n minus 1, n plus 1. And this is for a similar reason. We have n minus 1 rights and n plus 1 ups. And there are two n choose n minus 1 ways to arrange these. And if you expand this, you get, I'm not going to do the expansion, but it reduces to 1 over n plus 1 times 2n choose n. And apparently, it's often taught along with Catalan numbers that this is the same as the number of arrangements of n open parentheses and n close parentheses, so that at any point, the number of open parentheses is at least the number of closed parentheses. But I think this is just an equivalent formulation of this path that would appear much less often, so I don't think it's important to think too much about that. And a completely different scenario that gives the same sequence is the number of non-overlapping triangulations. And what that means is that, for example, if you have an octagon, you have a way to divide this into 8 minus 2, I think, triangles, such that none of these triangles overlap. One way to do that would be like this. um, Something like that, where you have one triangle here, etc. And none of these triangles overlap at anything more than an edge or a vertex. And the reason for this is that if you think about this recursively, you can consider where one of the edges from a certain vertex goes, and that will divide the polygon into two parts. And then you can apply the formula recursively on each part. So if f of n is this number, the recursive relation you will recover is that f of n is f of 0 times f of n minus 1 plus f of 1 times f of n minus 2, etc. And it goes all the way up until f of n minus 1 times f of 0. And it turns out that this formula also satisfies the same property. So from there, you just need to verify that they are the same for some base case, which you can just use n equals 3 for. And then you have that the numbers are the same. The Catalan numbers also have many other applications. I don't know many of these, but if you're interested, you can search up Catalan numbers. And the results will be very interesting. And if you list the first few out, they look something like 1, 1, 2, 5, 14, 42, 132, etc. Again, you usually don't need to know this part, only the first few numbers. And now I'm going to use this to go do one last problem, which it asks for the number of permutations of n integers such that there's no decreasing subsequence of length 3. What the decreasing subsequence parts means is that you don't have for any three numbers you consider in order, let's say 3, 1, 2, this is not in decreasing order. And we can check by hand if we are interested that for this given example, there is no such group of three numbers that are in decreasing order. but that's not too important, so I'm not going to do it. Instead, we can start by thinking about something very important in both computational and non-computational combinatorics, which is working for small cases. The smallest such n for which this problem would make any sense is if n equals 3. There are 6 permutations of 3 elements, and the only one where there is a decreasing subsequence uh, is 3, 2, 1, because that is in decreasing order. So that gives 5 permutations. Now we can consider n equals 4. And here, it's not too easy to think immediately about how you would approach this, but we can notice that there's just not that many permutations, and we can do this by some sort of brute force. So what I did is you can consider what the first element is. If it starts with 1, that's not going to contribute to any decreasing subsequence. So in fact, we're ordering 2, 3, 4, and all 5 of the above ways will work. 2 will also not have any decreasing subsequences because only one number is smaller than it, but it is the leftmost. So again, there are 5 ways to order the remaining elements. For 3, it's a bit different now because we can have a 3, 2, 1 in there. That means that 1 and 2 have to be in that order, and then the 4 can go anywhere. And there are 3 ways to do this. For 4, if there's any inversion, which means swapped element, in the remaining 3 numbers, such as if we have 1, 3, 2, and 3, 2 is swapped, then combining that with 4 will give a decreasing subsequence. So only 4, 1, 2, 3 works, and that's 1. If we add these, we get 14. And this is why I think it can be important to be familiar with the values of these sequences at small numbers, because you see 5 and you see 14, and you can think, is this the Catalan sequence? And one thing that I think is very convenient to do in a situation like this is try to make the problem make some sort of sense even when n is less than 3. And you can think about this as, for a permutation on 2 elements, we just do not have any restrictions because there's not going to be any group of them, any group of 3 at all. So there's not going to be any decreasing subsequence of length 3. So there are 2 permutations, and each works. Similarly, for n equals 1, there's 1 permutation, and that also works. N equals 0 is always a weird case to consider for these types of problems, but typically the answer will always be 1 for it because you're not actually choosing anything, so you just don't do anything, and that's your only choice. If this is confusing, it's usually not too important to consider it. It's just something I like to do. And if we look at our first few numbers, now that we have our additions, it's 1, 1, 2, 5, 14, which is even more promising because it's all of these 5. It could theoretically be possible to compute this for 5 if we care enough to try to verify it for 42, but this is good enough evidence that we should be convinced this is the Catalan sequence, and there's no need to spend too much time trying this for n equals 5. In fact, this problem asks you for a general n, which will not show up on a computational contest, because there you'll have a specific n to do it for. And if you have a specific n, you can just guess that the answer is the nth Catalan number, and just answer with whatever 2n choose n times 1 over n plus 1 is. And if this is a computational contest and you don't have too much time to think about this problem, you could just stop there and be done. But I think it's equally as interesting to see how if you wanted to actually solve this problem, and be more confident in your answers, especially because the AIME is a 3-hour test. It's also interesting to see how knowing that this is going to be the answer will impact your approach. And I don't think it was too impactful in my next step, which was more influenced by the type of thinking I did for the n=4 case. There, we considered what the first element is. Here, I did basically the same thing, but for the last element. It's not a huge difference, it just felt more convenient to me. So let's say we have some number of elements, and let's say A is the last element. Now suppose B is the second to last element. If B is greater than A, we can't have any C greater than B to the left. But all elements are to the left of it, other than B and A themselves. So that implies B is equal to N. Otherwise, we can sort of ignore the A because no decreasing subsequence can contain both the B and the A, since A is greater than B. And if any decreasing subsequence ends with A, let's say there is some D and C here. I'm actually going to say E and D because I already use C. If E, D, A is decreasing, so is E, D, B. So we can define for convenience f of n and a to be the answer for n elements where a is the last one. Then f of n a is f of n minus 1 1 plus f of n minus 1 2 until f of n minus 1 a minus 1. And there's also the case where b equals n. But then no decreasing subsequence can contain b. So if we just delete it, it's the same as f of n minus 1a. And I actually don't remember when I was doing this which direction I went, but you could motivate this if you look closely at these numbers 1, 3, 5, 5. Because if you have n equals 1, there's just 1. And this is a equals 1, a equals 2, a equals 3, a equals 4. For n equals 2, it's just 1 and 1. For n equals 3, it's 1, 2, 2, because this is where the exception 3, 2, 1 occurs. And for n equals 4, it's 1, 3, 5, 5. And yeah, I think that when I was doing this problem, I wrote this down first and realized that 3 is 1 plus 2, 5 is 1 plus 2 plus 2, etc. And I also noticed it was true for the above row, so that's what clued me in that this approach would be helpful. But even then, we have the summation, but it's not too clear what we're supposed to do from here to finish. And now is when you can think back to what the answer should be. The answer should be Cn, where Cn is the nth Catalan number. And it's a bit weird to think that how does this come from what we have right now? But then you can think about what the nth Catalan number actually means. As we first defined it, it's the number of paths along this square grid that never go above a diagonal. It currently is the number of paths on this subpart of the grid with no restrictions, as long as it only goes up and right, because then nothing above the diagonal is even included. And I don't think I would ever have come up with this if I didn't know the answer was supposed to be the nth Catalan number. But now we can think about this in terms of a path. Specifically, we can start by rewriting this as f of n a minus 1 plus f of n minus 1 a, which follows by taking this term out of the sum and applying the equation on a minus 1. So this is a sum of this and this, but the up direction is not in the grid, so it's not included. 5 is now the sum of 3 and 2, 3 is the sum of 1 and 2, etc. 1 is the sum of 1, and then we can keep drawing this in. And since it all comes down to 1, we have that f of NA is the number of paths from so f of NA is the number of paths from, what is this? NA to 1, 1. Okay. And this isn't quite finishing because we have paths from here, from here, from here, and from here. And now we have a way to find all of them, but we care about their sum, so this is still a bit annoying. But also, we only have 3 dimensions here, and we're considering n equals 4. And we know it should be the 4th Catalan number, which means we need a 4th dimension. And how we can resolve this is by now thinking about what the 5th row will look like. And now I'm going to draw dots instead of numbers because we saw that we can think about this in terms of a grid. So we have a bunch of paths. And we want to think about this in terms of the number of paths from 5, 5 to the number of paths of 1, 1, because that is what we know is the nth Catalan number, the 4th Catalan number. But this tells us that C4 is equal to f of 5 and 5. We care about the sum of of F4A. But now we can think back to this property, which tells us that f of 5, 5 is equal to f of 4, 0, plus f of 4, 1, plus f of 4, 2, plus f of 4, 3, plus f of 4, 4, which is just the total number of desired permutations on 4 elements. So the answer is Cn equals 2n choose n times 1 over n plus 1 as desired. And this is a very nice approach because you start by working on small cases that are much more feasible, and they sort of give you an intuition. And using that intuition, you can think about what approaches you might want to think about. And if you're stuck at some point, you can think about what the final answer should look like based on what the answer will be, and how you can try to fit your approach into that answer, which we did, for instance, by thinking about this in terms of paths, and by adding the 5th row, and even by thinking about working on the last element in the first place, because we noticed the property about the sums. So I think the most important takeaway from this problem is that it's very helpful to work on small cases of a problem, and also to be very organized about how you work on these small cases. Because if you don't write out the numbers in this way, maybe you won't see the idea, maybe you will, but either way, it's going to be harder. And this is the key ideology behind basically thinking about combinatorics problems as looking for patterns and trying to show that they work. Are there any questions? Okay, then that is all. Thank you for joining, and bye.